Hello, and welcome to Beyond the Last Star. Wherever you are right now, whatever kind of day it has been, you made it here. And that is enough. Find a comfortable position. Let your body settle. If you can, turn the lights down low or off completely. Because tonight, we are not staying here. Tonight we are going somewhere most people never think to go. Past the last planet, past the edge of the sun's reach, into the deep and patient dark where the real universe begins. Before we leave though, drop a comment and tell me where in the world you are listening from right now and what time it is there. I read every single one. There is something I love about knowing that people from every corner of this small blue planet are drifting off to the same stars at the same moment. And if this is your first time here, welcome home. Hit subscribe so the next journey finds you. Now, are you ready? Let's go. Your day is done. Whatever it held, the noise, the rushing, the small weight of 1,000 ordinary things, you can set it all down now. Tonight we are going somewhere, not far in the way that distance usually works. Not to another planet, not to another galaxy, not to the edge of the observable universe. Tonight we go to the nearest star, the closest sun to our own, the star that is, by the standards of the cosmos, practically next door. And in the going, we are going to discover something about the word close that changes what that word means forever. The nearest star to our sun is called Proxima Centauri. It sits 4.2 light-years away. 4.2 light-years. Astronomers call it our nearest stellar neighbour, our closest companion in the vast dark. And the first time you hear that number it sounds almost manageable. 4.2, not thousands, not millions, not billions, just 4.2. You could be forgiven for imagining that 4.2 light-years might be crossable, that it might be daffles, that it might be the kind of distance that a determined civilization could cover in a reasonable amount of time, that we might be closer to another sun than we are to the edge of any meaningful possibility. You would be wrong, and understanding why you are wrong, sitting with the actual meaning of that number, letting it settle into you slowly, the way all true things settle, is one of the most quietly humbling and strangely comforting experiences the universe has to offer. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In 1 second, it could circle the Earth 7 times. In 8 minutes, it travels from the Sun to Earth. 93 million kilometers covered in 8 minutes. In 1 year, light travels approximately 9.5 trillion kilometers. 9.5 trillion. Written out in full, that number has 13 digits, and most of them are zeros, and it represents the distance light covers in a single year of continuous travel. At the fastest speed the laws of physics permit. Proxima Centauri is 4.2 of those years away. Multiply 9.5 trillion by 4.2 and you get approximately 40 trillion kilometers. 40 trillion kilometers of empty space, cold and dark and almost entirely featureless, separating us from the nearest star. Now consider this. Voyager 1, the fastest and most distant spacecraft humanity has ever launched, has been travelling since September of 1977. It has been in continuous flight for nearly 50 years, moving at roughly 61,000 kilometers per hour. It is currently about 24 billion kilometers from the Sun, which makes it the most distant human-made object in existence. We are rightly proud of this achievement. It is one of the great feats of human engineering and determination. And at its current speed, it would take Voyager 1 approximately 73,000 years to reach Proxima Centauri, if it were heading in that direction, which it is not. 73,000 years. More than 10 times longer than all of recorded human history, longer than our species has been doing anything that leaves lasting archaeological evidence, longer than every civilization, every empire, every language, every war, Every discovery in all of human experience combined, multiplied by 10. This is what 4.2 light-years actually means, not a manageable distance. Not something that patience alone can bridge, something genuinely, structurally, almost inconceivably far away. And it is the nearest star. Breath, inhale, slowly, exhale. Let the scale of that settle. The reason this matters, the reason it is worth sitting with in the dark, at the end of a day, as the body grows heavier and the mind grows quieter, is not that it makes us feel small. It is that it tells us something precise and important about where we are in the story. We are a civilization that has just barely left its home. We have sent a few machines a short distance into the dark. We have put people on the moon, which is 384,000 kilometers away. A number that sounds large until you realize it is less than 1% of 1% of 1% of the distance to the nearest star. We are very early, we have barely opened the door. But let us go to Proxima Centauri anyway, in the only way we currently can. In thought, in the imagination, carried by everything science has learned about what is there, let us cover the distance the slow way, noticing what is along the path, arriving eventually at the small red star that has been burning quietly in the dark since long before our sun existed. The journey begins here, in the solar system, in the familiar neighbourhood of planets and moons and comets and the steady warm light of the sun. If you could somehow rise above the ecliptic plane, above the flat disk in which the planets orbit, and look down at the solar system from a distance, you would see a small bright star at the centre, and circling it, at various distances, 8 planets and their moons, a scattered belt of asteroids, a vast disk of icy objects beyond Neptune, and the faint ghostly suggestion of the Oort cloud, extending outward for perhaps a quarter of the way to Proxima Centauri itself. The solar system, from this vantage point, looks orderly and compact. Everything is moving, the inner planets swinging in tight, fast orbits, completing their loops in months. The outer planets moving more slowly in wider arcs, taking years or decades for a single orbit. Saturn's rings catching the sunlight, Jupiter's storm systems rolling across its cloud tops, Earth, small, blue, almost impossibly detailed from a distance, turning on its axis, its thin atmosphere holding the weather that makes everything on its surface possible. And then you leave the solar system behind, passing through the Kuiper belt with its frozen objects, crossing into the heliosheath where the solar wind slows and thins against the pressure of the interstellar medium, and finally through the heliopause, the boundary where the sun's influence ends and the space between the stars begins. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. On the scale of the journey to Proxima Centauri, that crossing represented roughly 1/600th of the total distance, less than 0.2% of the way. And it took 35 years. The space you enter beyond the heliopause is the interstellar medium, the thin, cold, almost empty material that fills the galaxy between the stars. It is not nothing. It contains hydrogen and helium at extraordinarily low densities, perhaps 1 atom per cubic centimetre. It contains magnetic fields too weak to deflect a compass needle. It contains cosmic rays, high-energy particles from distant stellar explosions, moving at nearly the speed of light in every direction. And it contains an almost total absence of anything else. No warmth, no landmarks, no directional cues except the faint pull of distant masses. Just dark, cold, thin gas, stretching in every direction for distances measured in light years. You travel through this for a long time. At Voyager's speed, the journey through interstellar space toward Proxima Centauri would last 73,000 years. But let us travel faster in the imagination. Let us cover the distance in the time it takes to tell this story. Let the emptiness of interstellar space wash over you. Not terrifying, not threatening, but immense and patient and very, very still. Approximately halfway through the journey, something interesting happens. The sun behind you, our sun, the star that powers all of life on Earth, the center of the only solar system any human being has ever inhabited, is no longer obviously different from the other stars. It is still the brightest star in your sky, the one that stands out, the one you could still identify. But it is a star, a bright point, not a disk, not a source of warmth, a star among stars, distinguishable by brightness, but not by any other quality that your instruments can easily detect. Home has become a distant light, the thing that made you, the star that warmed the planet, that produced the oceans, that produced the chemistry, that produced you, is just one of many points of light in the dark. This is what distance does. It compresses the significant into a point. It strips away the warmth and the texture and the personal weight of things, leaving only their light. Everything that has ever mattered to you, every person you have ever loved, every place you have ever been, every moment of joy and every moment of grief, every small Tuesday afternoon, and every important decision, all of it from halfway to Proxima Centauri, fits behind a single bright star in the darkness ahead of you. This is not sad, or not only sad, there is something clarifying about it. Something that helps the mind release what it has been gripping too tightly. When you understand that everything you have ever known is a pale blue dot orbiting a star that looks from a moderate distance like just another star, the urgency of most things dissolves, not the importance. The things that matter still matter, but the urgency, the pressure, the sense that this particular moment carries the weight of all possible moments. That pressure eases, and something else, something quieter and older and more honest, takes its place. You continue, and ahead of you, growing slowly brighter, is Proxima Centauri. It is not what you might expect if you were imagining another sun, another yellow star similar to our own, warm and generous and steady. What you find is something quite different. Proxima Centauri is a red dwarf. It is small. It contains about 1/8 of the mass of our Sun. Its surface temperature is roughly 3,000 degrees Celsius, compared to the Sun's 5,500. This makes it appear reddish-orange rather than yellow-white. And it is dim. So dim that despite being the nearest star, it is invisible to the naked eye from Earth. You cannot see our nearest neighbour on even the darkest, clearest night without a telescope. It is simply too faint. Red dwarfs are the most common type of star in the Milky Way. They make up roughly 70% of all stars in the galaxy. They are small, cool, and extraordinarily long-lived. Where our Sun will burn for about 10 billion years total, a red dwarf like Proxima Centauri may burn for 1 trillion years or more. 1 trillion years. The current age of the universe is 13.8 billion years. A red dwarf has a potential lifespan roughly 70 times longer than the universe has currently existed. They are the most patient things in the cosmos. Proxima Centauri is actually part of a triple star system. It is gravitationally bound to 2 other stars, Alpha Centauri A and Alpha Centauri B, which orbit each other in a binary pair about 23 light days away. From the surface of a planet orbiting Proxima, these 2 companions would appear as 2 very bright stars in the night sky. Not bright enough to light the ground, but blazing, like 2 brilliant jewels hanging together in a sky already rich with stars. Proxima is the closest of the 3 to Earth, which is why it bears the Latin name it does. Proxima means nearest. In 2016, astronomers announced a discovery that changed the conversation about this system. Proxima Centauri has a planet. It is called Proxima b, and it orbits its star in what astronomers call the habitable zone. The range of distances from a star where liquid water could theoretically exist on a planetary surface, given the right atmospheric conditions. For Proxima Centauri, that zone is much closer in than Earth is to our Sun. Because Proxima is so much dimmer and cooler, Proxima b orbits its star once every 11.2 days, at a distance of about 7.5 million kilometres, compared to Earth's 150 million kilometres from the Sun. But because Proxima is so much less luminous, those 7.5 million kilometers might provide roughly the right amount of warmth. Might. That word carries a great deal of uncertainty. The habitable zone is a useful concept, but it is only a starting point. A planet in the habitable zone is not automatically habitable. It also needs an atmosphere of the right composition to trap heat and provide pressure. It needs liquid water, which requires not just the right temperature, but the right pressure, the right chemistry, the right geological history. It needs protection from the radiation and stellar flares of its host star. And here, for Proxima b, the picture becomes more complicated. Red dwarfs like Proxima Centauri are prone to violent stellar flares. Unlike our relatively stable Sun, Proxima regularly produces enormous bursts of ultraviolet radiation and charged particles. Flares that, relative to the star's ordinary output, are far more intense than anything our Sun produces. A planet as close as Proxima b would be exposed to these flares repeatedly, potentially hundreds of times per year, without a strong magnetic field and a thick atmosphere. This radiation could strip the planet of its air over geological time, the way Mars lost its atmosphere to the solar wind after its own magnetic field weakened. Whether Proxima b has retained an atmosphere, and if so, what kind, is one of the most important open questions in planetary science. The James Webb Space Telescope has been observing Proxima Centauri and its system in 2025 and 2026, searching for signs of an atmosphere around Proxima b. The measurements are difficult. The planet is so close to its star that separating their light requires extraordinary instrumental precision. The results so far are ambiguous. There is no confirmed detection of an atmosphere, but also no definitive ruling it out. The search continues. It is the kind of search that could end in one of only two outcomes, each of them equally extraordinary. Either we find evidence that the nearest star has a world capable of supporting life, which would transform our understanding of how common habitable worlds are, or we find that even our nearest neighbour does not have such a world, which would tell us something equally important about the challenges that planetary habitability faces in the most common type of stellar environment in the galaxy. Proxima b is also thought to be tidally locked to its star. Tidal locking is what happens when a planet orbits so close to its star that the gravitational tug keeps one face always pointing toward it. The same side always in daylight, the other always in darkness, with a narrow twilight zone between them. This is the situation of our own moon relative to Earth. We always see the same face of the moon because it is tidally locked to us. A tidally locked planet around Proxima Centauri would have a permanent day side, blazing hot, bombarded by stellar radiation, a permanent night side, frozen and dark, and between them, a thin ring of perpetual twilight where temperatures might be moderated. Where if an atmosphere exists to distribute heat from day side to night side, liquid water might persist. Imagine standing in that twilight zone. The Sun, Proxima Centauri, would hang permanently near the horizon, large and reddish orange, never rising and never setting, casting long shadows across a landscape lit by an eternal rust-coloured dawn. The sky would be a different colour than Earth's, where our sky is blue because our sun's light is scattered by our nitrogen-oxygen atmosphere. The sky of Proxima b, if it has an atmosphere, might be tinged differently depending on the atmospheric composition. The nearby binary pair of Alpha Centauri A and B would be visible as two brilliant stars, depending on their position in the sky at any given time in the year, and the stars themselves, the stars of the night-side sky, which would be visible from the permanent dark half of the planet, would include, among the brightest points of light, a star called the Sun, the star that warmed the world, where something eventually wondered about all of this. Whether anything lives on Proxima b, whether anything has ever lived there, whether anything could ever live there, we do not know. The question is real. It is not science fiction. It is a legitimate scientific inquiry being pursued with real instruments making real measurements at a real star, 4.2 light-years away. And the answer, when it comes, will be one of the most significant pieces of information our species has ever received. But let us not rush to the answer. Let us sit in the question for a while. The way you sit in a dark room at the end of the day. Not anxious for morning, not rushing towards sleep, just present in the pause between things. The question of whether life exists at Proxima Centauri is beautiful precisely because it is open. Because it has not been answered. Because every night when the sky is dark and clear, there is a direction you could point. Toward the constellation Centaurus in the southern sky, toward a point of light invisible to the naked eye, and know that the question is there, waiting, real, hanging in the dark 4.2 light-years away. Now let us think about how we might actually go there, not in 1,000 years, not in science fiction, but with physics and engineering that exists now, or that is within reach of the next generation of technology. What would it actually take to cross 4.2 light-years in a time that matters to a human civilization? The spacecraft that would do this job does not resemble anything we have built before. It would not be large. It would not carry passengers, at least not in the first generation. It would be a probe, small, light, designed for speed above all else. The limiting factor in interstellar travel is not engineering complexity in the usual sense. It is energy, covering 4.2 light-years in any reasonable time frame requires travelling at a significant fraction of the speed of light, and accelerating any significant mass to a significant fraction of the speed of light requires an almost incomprehensible amount of energy. Consider, to reach 10% of the speed of light, about 30,000 kilometers per second, a spacecraft carrying only 1 kilogram of payload would require energy equivalent to roughly 8 times the annual electricity consumption of the United States. For a spacecraft carrying 100 kilograms, that number increases 100-fold. The energy requirements scale brutally with mass, which is why every serious proposal for interstellar travel involves making the spacecraft as small and light as physically possible. One of the most serious current proposals is called Breakthrough Starshot. It was announced in 2016 by the late Stephen Hawking, the entrepreneur Yuri Milner, and a team of physicists and engineers. The concept is to build a ground-based laser array of extraordinary power, a kilometre-scale array of lasers that could focus an enormous beam of light on a tiny spacecraft. The spacecraft would be a chip, literally a computer chip, a few centimetres across, attached to a thin reflective sail. The laser would push this sail to perhaps 20% of the speed of light within minutes of launch. At that speed, the journey to Proxima Centauri would take about 20 years, not 73,000 years, 20 years. The engineering challenges are real and significant. A laser powerful enough to push something to 20% of the speed of light would need to deliver about 100 gigawatts of power, roughly 10% of the total electrical generating capacity of the United States, focused into a beam that remains coherent over the light minutes of distance required for the acceleration phase. The sail material would need to withstand this intensity without burning. The chip itself would need to be engineered to survive the interstellar medium at a fifth of the speed of light. Each hydrogen atom in the interstellar medium would impact it with the energy of a cosmic ray particle. Communication with Earth from Proxima Centauri would face the constraint of the speed of light. Any signal sent would take 4.2 years to arrive. These are not fictional problems. They are real engineering challenges being worked on by real teams at real institutions. The timescale for solving them is measured in decades, not centuries. Some of the people working on Breakthrough Starshot today may live to see a laser array capable of sending a small probe to another star. Whether the political and economic will exists to build such a thing is a separate question. But the physics permits it. The concept is sound. A spacecraft travelling at 20% of the speed of light would cross the space between Earth and Proxima Centauri in about 21 years. During that journey, it would encounter the interstellar medium that Voyager 1 entered, pass through the heliopause of Proxima Centauri as it approached, enter the gravitational territory of the new star system, and potentially, if its instruments are working, if its power supply has lasted, if the design has survived the radiation environment and the particle impacts of interstellar travel, fly past Proxima b and send back images. Those images would take 4.2 years to reach Earth. A person who watched the launch in middle age might, if they lived long enough, see the arrival images before they died. A person born the year of the launch would be in their 20s when the probe arrived at Proxima Centauri. Their children might receive the first close-up images of a world around another star. This is not the distant future. This is the near future, if the will exists to pursue it. This is what 4.2 light-years looks like when viewed through the lens of what our physics actually permits. Breath, slowly in and out, feel the distances settling. But what if we wanted to send people? Not a chip on a sail, but human beings, living, conscious, curious, capable of doing science that no automated probe can replicate. What would that require? And what would it mean for the people who went? A spacecraft carrying humans to Proxima Centauri at 20% of the speed of light would still take over 20 years to complete the journey. That is a long time to be in space, longer than any current mission by a factor of dozens. The physical challenges are significant. Cosmic radiation exposure, bone density loss, muscle atrophy, psychological isolation, but they are not insurmountable. They are engineering and medical problems of a kind that can in principle be solved. The deeper challenge is social. Who goes on a 20-year journey and does not come back? Because coming back is not straightforward. The same journey that takes 20 years outbound takes 20 years to return. A round trip to Proxima Centauri takes more than 40 years. The people who left in their 20s would return in their 60s, if they returned at all. Everyone they knew before departure would be 40 years older. The world they returned to would be unrecognizable in many ways, and the people who stayed behind would have spent 40 years with only the slowest possible communication. Any message taking 4.2 years to arrive, any reply taking 4.2 years to return. There is a word for this kind of journey. Not a round trip, not an expedition from which you return to tell your story. A one-way crossing, a departure with no meaningful return. The word for the people who make such a journey is not explorers in the traditional sense. It is something closer to founders. They leave not to discover and come back, but to go and stay, to be the first presence of life from Earth in another star system, to begin something new rather than to report back to something old. Whether any human beings will ever make that crossing is not knowable from here. But the question is real. It is one of the genuine open questions about the long-term future of our species. Whether we remain confined to this solar system, extraordinarily rich, extraordinarily diverse, capable of supporting billions and eventually trillions of lives across planets and moons and habitats of every kind, or whether some portion of us eventually makes the crossing to other stars and plants something of us there, permanent and irretrievable. Both futures are imaginable. Both are consistent with what physics permits. Neither is guaranteed. What the distance to Proxima Centauri tells us, perhaps more than anything else, is that we are genuinely early. We are a civilization that has existed for a few thousand years in a galaxy that is 10 billion years old. We are a technological civilization, capable of rocketry and space travel and telescopes and computers. For less than a century, we have been sending radio signals into space for about 100 years, which means our electromagnetic presence extends only 100 light-years in any direction. In a galaxy 100,000 light-years across, We are a new and very small voice. The distance to the nearest star puts this in perspective. We have not reached even the nearest star. We have not confirmed whether the nearest star has a habitable world. We do not know whether we are alone in the galaxy or whether the galaxy is full of life. We are very early in the story. The story has barely begun. And somehow that is one of the most restful thoughts imaginable. The pressure of being significant, of being the culmination of something, of needing to have figured things out. It eases when you hold the actual scale of things. We are early, we are small, we are one of the first chapters of a story that will go on for longer than we can meaningfully imagine. The things we have not yet discovered outnumber the things we have. The distances we have not yet crossed dwarf the distances we have. The questions we cannot yet answer are more interesting than the ones we can. 4.2 light-years. Our nearest neighbour, a small red star burning patiently in the dark, surrounded by at least one planet, perhaps more, in a system we have barely begun to study. A destination that our fastest spacecraft would take 73,000 years to reach. A crossing that our physics suggests could be made in 20 years if we build the right tools. A place that might be empty or might not be, that we cannot visit in any physical sense in any living person's lifetime, but that we can study, that we can aim our best telescopes toward, that we can send our smallest, fastest probes toward, and that we can think about on quiet nights when the scale of things becomes not frightening but clarifying. The stars are patient. The nearest one has been burning for longer than Earth has existed. Proxima Centauri is thought to be about 4.8 billion years old, slightly older than our Sun. It will continue burning for nearly 1 trillion more years. Whatever we eventually do about the distance, whatever technology we build, whatever choices we make, whatever crossings we attempt, Proxima Centauri will still be there, still burning, still patient, still 4.2 light-years away from a small blue world where something once looked up and started wondering what was out there. The wondering is the beginning, and beginnings in the long story of the universe are precious things. The room around you is quiet. The day is far behind you now. The distances we have travelled tonight, in thought, in imagination, in the honest accounting of how far the nearest star actually is, have done what distances do when you let them. They have put things in proportion. They have made the urgent feel smaller and the patient feel larger. They have reminded you that the universe is very large and very old and very full of things still to be discovered. And that wherever you sit in that story, you sit somewhere interesting, somewhere early. Somewhere that still has most of the story ahead of it. 4.2 light-years away, a small red star burns on. It has been burning your whole life. It will burn through everything you will ever do. And somewhere in the system around it, a planet turns, or does not turn, held in place by tidal locking, beneath a sky where our own sun is just another star, where Earth is invisible, where the entire history of human civilization is a faint trace of radio waves that have not yet arrived, the nearest star. Not close at all, and yet, somehow, knowing it is there, knowing its name and its mass and its planet and the precise number of light-years that separate it from this room, makes the dark above you feel less empty and more interesting, less threatening and more full, less like a void and more like a question hanging patiently in the dark, waiting for us to find the tools to answer it. Rest now. The stars are burning. The distances are real. And tomorrow night there is more of the universe waiting. Stranger further, more full of wonder than any single night can hold. There is a particular kind of silence that exists between the stars. Not the silence of a quiet room, or the silence of a forest at night, or even the silence of a mountaintop above the clouds. Those silences still contain things. Air moving, distant sounds carried on the wind, the small sounds of your own body, breathing and circulating. The silence between the stars contains almost none of that. It is a silence so complete that the word silence barely covers it. It is an absence so total that it becomes a presence of its own. Something you would feel if you were somehow out there, not as quiet but as a quality of space itself, a texture to the emptiness that is different from anything experienced on Earth. Proxima Centauri sits in that silence. It has been sitting in it for nearly 5 billion years, long before Earth formed, long before the Sun ignited, long before any of the chemistry that would eventually produce living things had been assembled in any corner of this galaxy. Proxima Centauri was already burning, already turning, already patient in the dark, its small red light going out in all directions into the interstellar medium with complete indifference to whether anything anywhere would ever receive it. And yet the light went out, as it always does, because that is what light does. It travels regardless of destination, regardless of whether any eye or instrument is waiting at the other end. The photons leave the surface of Proxima Centauri, and they travel outward through the thin gas of the interstellar medium, through the boundary of whatever heliosphere. Proxima generates around itself, out into the open space between the stars. Some of them, over billions of years, have travelled in the direction of our solar system. Some of those, more recently, have been intercepted by telescopes, and a very few of them, the ones that arrived at exactly the right angle, at exactly the right time, have been focused onto the detectors of instruments, sensitive enough to measure them, and the information they carry has been converted into numbers, and those numbers have been turned into knowledge. We know Proxima Centauri because its light reached us, the same way we know everything we know about the universe, because light, patient and indifferent and fast beyond any other thing, crosses the distances and arrives, carrying what it can carry, telling what it can tell. The light from Proxima Centauri that you could theoretically detect tonight left its surface 4.2 years ago, which means you are always looking at Proxima as it was 4 years in the past. You cannot see it as it is right now. No one on Earth can. Whatever is happening at Proxima Centauri in this exact moment will not be known here for 4.2 years. Not because our instruments are inadequate, but because light itself takes that long to make the crossing, and nothing we know of travels faster than light. The universe enforces a delay on all of its communications. Nothing happens instantly across distance. Everything takes time. The further apart two things are, the older the news when it arrives. This is one of the deepest features of the universe, and one of the least intuitive. We are accustomed to thinking of information as something that can travel instantaneously. You send a message and it arrives. You look at something and you see it as it is. But this intuition breaks down at astronomical distances. At 4.2 light years, the delay is 4.2 years. At 26,000 light years, the distance to the galactic center, the delay is 26,000 years. At 2.5 million light years, Andromeda, the delay is 2.5 million years. The universe we observe is not the universe as it is. It is the universe as it was, at different times in the past, all arriving simultaneously at the surface of our instruments, all mixed together into a single image we call the present sky. Proxima Centauri, as it was 4 years ago, is a dim red star in a quiet patch of sky in the constellation Centaurus, visible from the southern hemisphere, invisible to the naked eye, orbited by at least one planet and possibly more. Whether that is still true, whether Proxima b still exists, whether no asteroid or rogue body has altered the system in the 4 years since we last received light from it. We genuinely do not know. We are almost certainly fine. Systems like this are stable over timescales of billions of years, but strictly speaking, we are always looking at the past, always reading a message that was sent before we received it. The universe communicates in delay, and we have no choice but to listen on its terms. What we have learned from the light that has reached us is considerable. Proxima Centauri has a mass of about 12% of the Sun's mass. Its radius is about 15% of the Sun's radius. Its luminosity, the total amount of energy it puts out, is only about 1/6 of 1% of the Sun's luminosity. It is by almost every measure a humble star, small, dim, cool, and extraordinarily common. There are more stars like Proxima in the Milky Way than any other type. The dramatic, luminous stars that dominate the night sky, Sirius, Betelgeuse, Rigel, are the exceptions, the outliers, the unusual cases. Proxima-type stars are the norm. The galaxy is mostly made of dim, patient, long-lived red dwarfs, burning quietly in the dark. And Proxima is one of them, simply the one that happens to be nearest to us. The flares that Proxima produces are one of the most important considerations when thinking about the habitability of Proxima b. In 2016, a particularly powerful flare was recorded, one of the largest ever observed from Proxima Centauri, that briefly increased the star's ultraviolet output by a factor of roughly 68 times the normal ultraviolet radiation, delivered in a burst lasting only a few minutes, but intense enough that any planet without substantial atmospheric shielding would receive a significant radiation dose. On Earth, our magnetic field and thick atmosphere protect us from the worst of the Sun's occasional outbursts. Our ozone layer absorbs ultraviolet radiation that would otherwise be harmful to surface life. Proxima b, if it exists without these protections, would face a much harsher radiation environment than anything living things on Earth have ever had to cope with. But life is not fragile in the way we sometimes assume. Life on Earth has survived mass extinctions, ice ages, asteroid impacts, and periods of dramatically different atmospheric chemistry. Extremophile organisms, life forms adapted to extreme conditions, have been found in boiling hot springs, in the cores of nuclear reactors, in the ice of Antarctica, in the concentrated acid of sulfuric hot springs, in the crushing pressure of the deepest ocean trenches. Life, once it gets started, tends to find ways. The question of whether Proxima b's radiation environment would prevent the origin of life, or merely constrain its forms, or prove no obstacle at all to life that evolved in that environment from the beginning, is genuinely open. There is also the possibility of life underground, shielded from the stellar flares by kilometers of rock, or life in a deep ocean protected by the water above it, or life that has developed biochemistry adapted specifically to ultraviolet radiation. The way some organisms on Earth have adapted to use ultraviolet as a source of energy rather than a threat. The space of possible life-supporting conditions is much larger than the narrow range of conditions that humans require. We have a tendency to assume that habitable means habitable for humans. It does not. It means capable of supporting some form of chemistry complex enough to replicate and evolve, and the conditions under which such chemistry can operate are far broader than our own requirements suggest. Proxima b is approximately 1.1 times the mass of Earth, based on current measurements. This makes it what astronomers call a super-Earth, slightly larger and more massive than our planet, likely rocky, capable in principle of having a surface, an interior structure similar to Earth's, and possibly a magnetic field generated by a molten metallic core, whether it has water, whether it had water delivered by comets and asteroids in the early history of the system, or formed in a region water-rich enough to incorporate it, is not known. Water requires specific conditions during planetary formation, and the conditions around a red dwarf star differ from the conditions around a Sun-like star in ways that are still being studied. The James Webb Space Telescope, currently operating at a point about 1.5 million kilometers from Earth, has been looking at Proxima Centauri in 2025 and 2026 with instruments capable of detecting atmospheric signatures around nearby exoplanets. The technique it uses is called transmission spectroscopy. When a planet passes in front of its star as seen from Earth, starlight filters through the planet's atmosphere, and different molecules in the atmosphere absorb different wavelengths of light, leaving a characteristic pattern in the spectrum that the telescope can detect. If Proxima b has an atmosphere, and if it transits in front of its star from our vantage point, JWST might be able to detect it. The geometry is uncertain. Whether Proxima b transits, whether its orbit is inclined in exactly the right way so that it passes between us and the star, is not confirmed. If it does not transit, transmission spectroscopy cannot work, and different methods will be needed. But other upcoming telescopes, including the extremely large telescope currently under construction in Chile, may be able to directly image the light reflected from Proxima b's surface, which would allow atmospheric characterization even without a transit. The measurements are becoming possible that were impossible a decade ago. The answer to whether Proxima b has an atmosphere, and what that atmosphere contains, may be known within the next decade. If the answer is yes, there is an atmosphere, that alone would be extraordinary. An atmosphere means the planet has held onto its gas against the radiation pressure of its star, which suggests it has either a strong magnetic field or is massive enough to retain air, despite the stripping effect of the stellar wind, or both. And if the atmosphere contains oxygens, in combination with methane, two molecules that should react with each other and disappear quickly unless something is continuously replenishing them. The implication would be that something biological is producing them. That would be, by any measure, one of the most significant discoveries in the history of science. But even a simple atmosphere, even nitrogen and carbon dioxide with no biological signatures, would be meaningful. It would tell us that planets around red dwarf stars can hold their air, that the most common type of star in the galaxy can host planets with atmospheres, that the conditions for rocky planet habitability are more widespread than a pessimistic reading of the red dwarf flare problem would suggest. The absence of biology is not a failure, it is information. Every piece of information about the nearest star is precious beyond what its proximity alone suggests, because what we learn there is likely to be generalized, to tell us something about the billions of other red dwarf systems in the Milky Way, most of which we will never be able to study in comparable detail. The nearest star is a laboratory, not one we can visit in person, not one whose specimens we can hold and examine, but a laboratory nonetheless. The one cosmic environment outside our own solar system where we can gather the most detailed information, where our instruments have the best chance of detecting faintest signals, where the limitations of distance are at their minimum and the possibility of genuine discovery is at its maximum. Whatever we learn at Proxima Centauri is likely to echo outward across the entire field of exoplanet science, shaping how we think about habitability, about the frequency of life, about the prospects for other minds in this galaxy. The prospects for other minds. Let that phrase sit for a moment. Not the prospects for other organisms, for bacteria or algae or complex chemistry that self-replicates, but other minds, other things that look out at the universe and wonder, other beings that lie in the dark at the end of a long day and think about the stars. Whether such things exist anywhere else in the Milky Way is perhaps the deepest open question in all of science, and the nearest star, 4.2 light-years away, studied more carefully than any other stellar system outside our own, is one of the places where that question might first receive an answer. Not a definitive answer, not proof of minds, but evidence of conditions, or the absence of conditions, that would tell us something about the probability, something that would shift our estimate, however slightly, of whether we are alone in this galaxy, or whether the galaxy is full of the kinds of places where things like us could arise. Every data point from Proxima Centauri is, in a quiet way, a data point in that larger inquiry. The nearest star is not just a curiosity, it is a clue. Your breathing has slowed. The room is quieter than it was when this began. The day has moved further into the past, where it belongs, where it can no longer ask anything of you. The questions about Proxima Centauri, whether it has a habitable world, whether anything lives there, whether we will ever send anything there, are not questions that need to be answered tonight. They are patient questions, the kind the universe specializes in. They will wait. They have been waiting for 4.8 billion years already. They can wait a little longer while you rest. The nearest star is burning right now. Small and red and patient, 4.2 light years away, orbited by at least one world, surrounded by the thin silence of interstellar space. Its light is travelling in all directions, crossing the dark, some of it heading in our direction, some of it destined to arrive at our instruments 4.2 years from now, and in the system around it, whatever is there. Planet or ocean or bare rock, or something we have not imagined, continues doing what it does, indifferent to whether it is being observed, indifferent to the names we have given it, simply continuing in the patient way that all things continue when no one is asking them to stop. The Fermi paradox is named after Enrico Fermi, the physicist who, during a casual lunch conversation in 1950, asked a question that has never been satisfactorily answered. He had been discussing the possibility of extraterrestrial civilizations with colleagues, the probability that they exist, the likelihood that some of them would be technologically advanced, the possibility that some might have been spacefaring for millions of years. And then, in the middle of the conversation, he asked simply, "Where is everybody?" It is a question that gets more interesting the longer you sit with it. The Milky Way is roughly 10 billion years old. It contains between 200 billion and 400 billion stars. A substantial fraction of those stars have planets. A substantial fraction of those planets are in the habitable zones of their stars. Even if the probability of life arising on a given habitable planet is small, 1 in a million, 1 in a billion, the sheer number of opportunities across 10 billion years of galactic history suggests that life should have arisen many times. And if even a small fraction of those origins eventually produced technological civilizations, and if even a small fraction of those civilizations eventually developed the capacity for interstellar travel or communication, the galaxy should by now be full of evidence of their existence. Radio signals, physical artifacts, megastructures, something. We detect nothing. The sky is radio quiet. The solar system shows no signs of visitation by any non-human intelligence. The stars, examined in detail, show no obvious signs of being used by technologically advanced beings in ways that would be detectable across interstellar distances. Either technological civilizations are extraordinarily rare. Perhaps we are among the first, perhaps we are unique, or they exist but are not communicating in ways we can detect, or they exist but have chosen not to make themselves known, or there is some systematic reason why civilizations that reach our level of development do not survive long enough to become detectable. The question has no consensus answer. It sits, patient and uncomfortable, at the center of one of the most important discussions in science. The nearest star is relevant to this question in a specific and important way. If Proxima b turns out to be habitable, if it has an atmosphere, liquid water, the right chemistry, and if no life has arisen there after nearly 5 billion years, that would be a piece of evidence in favor of life being rare. A habitable world, sitting in a stable system for billions of years, and yet no biology. That would suggest that the origin of life is not automatic, that it requires conditions or events or circumstances more specific than simply having a wet, rocky planet at the right temperature. And if life is rare in that sense, then the absence of detectable civilizations in the galaxy becomes less puzzling. On the other hand, if Proxima b turns out to have signs of biology, even microbial biology, even the faintest chemical hint of living processes, then we would know that life arises independently in at least 2 places in the same small corner of the Milky Way. And if it arises twice in the same corner, it almost certainly arises throughout the galaxy. The nearest star would have told us that life is common. And then the Fermi paradox would become much more acute. Because if life is common, where are the civilizations? Where are the signals? Where is the evidence of something that has had millions of years longer than we have to develop technology and the means to spread it? These are questions that the nearest star might help answer, not definitively, not immediately, but incrementally. Each measurement of Proxima b adds a point of data to a problem that currently has almost no data points at all. We are reasoning about the frequency of life in the galaxy with a sample size of 1 Earth. Every additional data point, even an upper limit on what is present at Proxima b, changes the calculation. The nearest star is not just 4.2 light-years away. It is 4.2 light-years away from a much more accurate answer to some of the deepest questions we have ever asked. The Alpha Centauri system, the triple star system to which Proxima belongs, has its own story worth following. Alpha Centauri A and Alpha Centauri B, the two sun-like stars that orbit each other, are both of similar mass and temperature to our own Sun. They are about 4.37 light-years from Earth, slightly further than Proxima, but close enough that the whole system is considered our nearest stellar neighbourhood. The two main stars orbit each other at an average distance of roughly the distance between our Sun and Uranus. Close enough that they would significantly influence each other's planetary systems, making stable planetary orbits more complex than around a single star. Whether planets exist around Alpha Centauri A or B is a question that has been studied extensively and remains somewhat uncertain. In 2012, a planet was announced around Alpha Centauri B, a short-period rocky planet with a mass similar to Earth's. The announcement generated enormous excitement. A planet, potentially Earth-sized, at our nearest sun-like neighbour. The excitement faded when subsequent analysis suggested the signal was likely an artifact of the data analysis technique rather than a real planet. But absence of evidence is not evidence of absence. The Alpha Centauri system could have planets. We do not yet have instruments sensitive enough to definitively rule them out or to confirm their presence with confidence. The extremely large telescope, now under construction on Cerro Armazones in the Atacama Desert of Chile, will, when completed, have the capability to directly image reflected light from planets around Alpha Centauri A and B. Not in the distant future. The telescope is scheduled to see first light in the late 2020s. It would be the first instrument capable of directly seeing a planet around another sun-like star in reflected light, as opposed to detecting it through the dimming of the star during transits or the wobble it induces in the star's motion. A direct image, a point of light separated from its star that represents another world. This may happen within the decade. The nearest star system may show us another planet, or several, in the lifetimes of most people alive today. What we find there will matter. If the Alpha Centauri system is barren, if its complicated gravitational architecture has prevented stable planetary orbits, or if any planets that formed were stripped of their atmospheres, that tells us something about which stellar environments are most hospitable to planet formation. If we find rocky planets with atmospheres, that tells us something different. If, beyond all expectation, we find something that hints at biology, even something as subtle as an unexpected chemical signature that requires a biological explanation, the conversation will change in ways that are genuinely difficult to anticipate. Science does not always prepare you for its own discoveries. The detection of the cosmic microwave background was not expected by the people who made it. Two radio astronomers trying to eliminate what they thought was noise in their antenna. The discovery of the accelerating expansion of the universe was not what the teams measuring it were expecting to find. They thought they were measuring how much the expansion was slowing down. The discovery of hot Jupiters, massive planets, orbiting extremely close to their stars, overturned decades of models of how planetary systems form. When new data arrives from a genuinely new place, it almost always contains surprises. The nearest star system has not yet been studied with instruments capable of finding an Earth-like planet or characterizing its atmosphere. When we finally have those instruments, the surprises may be significant. You are lying still. Now the muscles that carried you through the day have surrendered their tension. The thoughts that felt urgent a few hours ago have drifted to a quieter place in the mind where they can wait without demanding attention. This is what the body knows how to do when given permission. Release. Let go. Trust that the world will continue without active supervision. The nearest star will still be there tomorrow. The questions about Proxima b will still be open. The Fermi paradox will still be unsolved. None of these things require your attention tonight to continue existing. The history of human curiosity about the stars is long. It predates writing. It predates cities. Long before anyone had a word for astronomy, before anyone knew what the stars were made of, or how far away they were, or how many there were. People looked up at night and felt something in response to the sky. Not just curiosity, something closer to recognition. Something like the feeling of being part of something very large that you cannot fully see. Every human culture across every era of recorded history has had some relationship with the sky. Some have used it for navigation, some for timekeeping, some for agriculture, some for religion, some for philosophy. But all of them looked. All of them felt something when they looked, and all of them passed this, looking on to their children, and their children's children, across generation after generation, until eventually some of those children built telescopes and launched spacecraft and pointed instruments at the nearest star, and began, for the first time in the history of the species, to actually measure what was there. That lineage from the first eyes that looked up to the first instruments that measured is one of the most remarkable threads in human history. It is not a thread that was pulled by any single person or any single civilization. It is a collective thread woven from the curiosity of billions of people across tens of thousands of years, each generation adding something. A new measurement, a new model, a new instrument that made the next generation's understanding slightly richer. The people building the extremely large telescope are the inheritors of everyone who ever looked at the sky and wondered what they were seeing, and the people who will use its data to characterize the atmospheres of planets around Alpha Centauri are inheritors of everyone who ever asked whether we are alone. This is one of the most beautiful things about science. Not that it has all the answers, but that it is genuinely cumulative. Knowledge accumulates. Each generation starts from a higher floor than the one before, the floor that we are standing on now. 400 years after Galileo first turned a telescope to the sky, 60 years after the first human beings left Earth, 30 years after the discovery of the first planets around other stars, is higher than any floor any previous generation has stood on, and the floor that the next generation will stand on will be higher still. Built on everything we are learning now about the nearest star and its possible worlds. The stars of the night sky are not just beautiful objects, they are questions. Each one is a sun, most of them with planets. Some of those planets perhaps with atmospheres. Some of those atmospheres perhaps with chemistry. Some of that chemistry perhaps organized into something that replicates and evolves, and eventually looks up. The night sky is a collection of open questions, each one hanging silently in the dark, waiting for the instruments that are patient enough and sensitive enough and close enough to begin to answer them. And the nearest question, the most accessible, the one that our best current technology is already reaching toward, hangs in the southern sky 4.2 light years away, small and red and burning, in patient silence. Proxima Centauri, our nearest neighbour, the first chapter of the interstellar story, already underway, already being read, already yielding its first careful words to instruments pointed at it, from a small rocky world where something learned to wonder. There is a thought experiment that physicists and philosophers sometimes use when discussing the nature of distance and time. Imagine you could somehow observe the Earth from Proxima Centauri. Not travel there, just watch. Using an instrument sensitive enough to detect the faint light reflected from our planet across 4.2 light-years of space, what would you see? You would see Earth as it was 4.2 years ago, not as it is now. The light carrying the image of Earth's current state has not yet arrived. It will not arrive for 4.2 years. What reaches your hypothetical instrument tonight is the Earth of 4 years past. A world slightly different from today's, carrying on its surface slightly different events, slightly different arrangements of human beings and weather systems and political situations. You would be watching a recording, not a live feed. The most current news from Earth would always be 4 years old by the time it reached you. Now extend this thought. If you could somehow see Earth from a star 1,000 light-years away, you would see it as it was 1,000 years ago. Medieval Europe, Song Dynasty China, the height of Mayan civilization. From 10,000 light-years away, you would see an Earth that had not yet developed writing. From 100,000 light-years away, at the far edge of the Milky Way, you would see an Earth before modern humans existed at all. From the Andromeda Galaxy, 2.5 million light-years away, you would see an Earth before our genus Homo had emerged. The universe keeps records. In the light travelling outward from Earth right now, in all directions, at the speed of light, is the complete history of everything that has happened here. Every event, every moment, every afternoon, and every catastrophe encoded in the electromagnetic radiation that our world has been emitting since it formed. That record is spreading outward at the speed of light, thinning as it goes, becoming harder to read with distance, but not disappearing. It is out there, moving, permanent in the sense that it cannot be recalled or erased. This is one of the strangest and most quietly moving facts about light and distance. Nothing that happens is truly gone. It persists, in principle, in the light that carries its record outward through the universe. A civilization with instruments sensitive enough. Impossibly sensitive, beyond anything physics currently contemplates. Could theoretically read any moment in Earth's history from the right, distance. The past is not over, it is just far away. And what is true of Earth is true of Proxima Centauri. The history of that star system is spreading outward in light right now, in all directions. The moments when Proxima's flares erupted, the seasons on Proxima b, if it has them, the chemistry of whatever exists on its surface, or in its atmosphere. All of it is travelling through space at the speed of light, most of it heading away from us, but some of it arriving. Each measurement our telescopes make of Proxima Centauri is a reading of its history, not its present, which has not yet arrived, but its recent past, 4.2 years gone. We are archaeologists of light. Everything we know about the universe is history. The universe as it is right now, in this exact moment, across all of space simultaneously. That is something no observer anywhere can ever fully know, because the information takes time to travel. Every civilization in the universe, wherever it sits, is necessarily looking at the past. The present is always local. Everything beyond arm's reach is history. There is something unexpectedly restful about this. The universe keeps its own records. The light from this moment, this specific night, your breath slowing, the room quiet, the stars burning above whatever clouds or walls separate you from the sky, is already travelling outward. It left the moment you began reading. It is spreading in all directions at the speed of light, carrying this moment outward through the galaxy, to places and times that will never be aware of it, that it will never reach in any meaningful sense, but that it is nonetheless travelling toward. The universe is paying attention in its own way. not with care or intention, but with physics. Physics records everything. Light carries it outward. The present moment is already becoming part of the permanent record of the universe, encoded in radiation spreading at 300,000 kilometers per second. In every direction from where you are, the nearest star burns. The light from it is already on its way here. The light from here is already on its way there. Both are travelling patiently at the only speed the universe allows for such things. 4.2 years in each direction, a slow correspondence between two stellar neighbourhoods that have been exchanging light since long before either had anything that could be called awareness. The exchange is still happening. It will keep happening. Nothing stops it. Now let the mind drift closer to the ground, back from Proxima Centauri, back through 4.2 light-years of interstellar space, back into the heliosphere, back into the solar system, back into the small blue world where all of this wandering takes place. The wonder itself is remarkable. The capacity to think about a star 4.2 light-years away, to calculate its mass and its temperature and the orbit of its planet, to design instruments to measure its atmospheric composition, to sit quietly in a dark room and feel something about the distances involved. This capacity is not guaranteed. It is not the automatic outcome of any physical process. It is something that emerged, slowly and improbably, over billions of years of chemistry and biology, and the particular history of one small planet around one ordinary star. The universe has been running for nearly 14 billion years. For most of that time, it contained nothing capable of wondering about itself. For most of that time, it was a collection of particles and forces and fields, evolving according to its own rules, producing structures of increasing complexity. Galaxies, stars, planets, chemistry, but not, as far as we know, producing anything that looked back. Then, at some point, the timing is uncertain, the mechanism not fully understood. Chemistry, on at least one small world, crossed a threshold and became biology. And biology, after billions of years of evolution, produced brains. And brains, after hundreds of thousands of years of development, produced the capacity for curiosity. And curiosity, after tens of thousands of years of practice, produced science. And science, in a few centuries of accelerating progress, produced the tools to measure the nearest star, from hydrogen to helium to heavier elements, to chemistry to biology, to brains to curiosity to telescopes to Proxima Centauri. That is a lineage. That is a sequence of transformations, each one building on the last, each one made possible by the ones before it. You are at the current end of that sequence, not the final end, the current end. The leading edge of a process that is almost certainly not finished. The capacity to wonder that you possess tonight, lying in the dark thinking about the nearest star, is the product of 14 billion years of cosmic history. It is, in a very real sense, the universe thinking about itself. The universe producing something capable of measuring its own contents and asking what they mean. That is not small. Even held against the scale of 100,000 light-years and 400 billion stars, that is not small. Size is not the only measure of significance. A galaxy is vastly larger than a brain, but a galaxy does not know it exists. You do, and the knowing, the capacity for it, the experience of it, is something that did not exist anywhere in the observable universe. For most of the time the observable universe has been running. It is new, it is rare as far as we know. And it is happening right now in you, in this quiet room, at the end of this ordinary day. The weight of the day is almost entirely gone now. The things that felt urgent have become what they always were. Temporary arrangements of circumstances, events in a story that is much larger than any single chapter. The nearest star does not know about your day. The interstellar medium does not care about the problems you solved or failed to solve. The slow turning of Proxima Centauri around the galactic centre is not adjusted by anything that happens on Earth. And that indifference is not cold. It is freeing. The universe does not require your involvement to continue being what it is. The nearest star will burn for nearly 1 trillion more years whether you worry about it or not. The questions about Proxima b will still be open tomorrow. The distances will still be real. And you will still be here. If you rest, if you let the day dissolve and the night do its quiet work, sleep is one of the most ancient things you do. Long before there were stars visible from wherever your ancestors lived, long before there were words for what they saw in the sky, they slept. The rhythm of sleep and waking is older than language, older than culture, older than the specific arrangements of atoms and experiences that make you who you are. It is a rhythm shared with almost every living thing on Earth, inherited from ancestors so distant that the word ancestors barely applies, built into the biology of consciousness as thoroughly as breathing is built into the biology of the body. You do not have to decide to sleep, you only have to stop resisting it. The nearest star is 4.2 light years away. You are here. The distance between those two facts is real and vast and quiet, and in the space between them, in the particular position you occupy, close enough to a warm yellow star to be alive, far enough from the nearest other star to have developed in relative calm, something has emerged that can hold both those facts at once and feel, in the holding of them, something that has no precise name but that is close to wonder, close to gratitude, close to the particular peace that comes from understanding your own smallness, not as a diminishment, but as a placement. Knowing where you are, knowing the scale of what surrounds you, knowing that the universe is very large and very old, and that you are a small and recent and improbable part of it. That is enough. That is more than enough. The nearest star is burning right now, not metaphorically, not as a figure of speech, literally, physically, at this exact moment, 4.2 light years away in the direction of a constellation in the southern sky. A small red star is fusing hydrogen into helium in its core, releasing energy that travels outward through its layers and emerges at its surface as heat and light. That light spreading outward in all directions through the thin silence of interstellar space, some fraction of it heading in the direction of this small blue world, travelling at the speed of light, arriving 4.2 years after it left, right now. As you breathe, as the room holds its quiet, the nearest star is burning. It has been burning for nearly 5 billion years, before the Earth existed, before the Sun existed, before our solar system had formed from the cloud of gas and dust that collapsed to create it. Proxima Centauri was already old when our world was new. It will still be burning when our Sun has exhausted its hydrogen and into a red giant, and the inner planets have been swallowed, and whatever remains of the Earth has been transformed beyond recognition. Proxima Centauri will still be burning then, and for hundreds of billions of years after that, and for close to 1 trillion years in total, from beginning to end, a lifespan so long that our Sun's entire existence, from its formation to its death, occupies less than 1% of it. Patient things outlast everything else. The interstellar space between here and Proxima is not empty in any total sense. It is filled with the thin gas and dust of the interstellar medium. It is filled with cosmic rays, travelling at nearly the speed of light in every direction. It is filled with the faint residual glow of the cosmic microwave background, the after-image of the Big Bang, present everywhere in the universe at a temperature just barely above absolute zero. It is filled with dark matter, whose presence is detectable only by its gravitational effects on everything around it. It is not a void. It is a very thin, very cold, very quiet medium, and through that medium the light from Proxima has been travelling since long before anything on Earth could see it. The first eyes that could detect Proxima Centauri's light were probably not looking for it. They were looking at the general sky, watching for threats, navigating by stars, observing the patterns of the heavens for religious or agricultural purposes. For most of human history, Proxima was simply part of the background glow of the southern sky, one of the innumerable stars that make up the rich band of the Milky Way, as seen from the southern hemisphere, indistinguishable from its neighbours, too faint for the naked eye, invisible in the ordinary sense of the word. It was not until 1915 that its proximity was established. An astronomer named Robert Innes, working in South Africa, found that a star in Centaurus had an unusually large proper motion. It was moving across the sky, relative to more distant stars, faster than almost any other star visible. Fast proper motion is usually a sign that a star is close. Nearby objects appear to move faster against a distant background, the same way a nearby tree flickers past your window, much faster than a distant mountain when you are in a moving vehicle. Innes measured the motion, calculated the distance, and determined that this faint red star was in fact the closest star to our Sun. He named it Proxima Centauri. Proxima being the Latin for nearest Centauri, referring to the constellation Centaurus in which it sits. For a century after that discovery, Proxima was known mainly as a curiosity. The nearest star, yes, but a dim and unspectacular one, seemingly the least interesting possible neighbour, a small red dwarf with no known planets, prone to flares, unlikely to be of any importance beyond its proximity. Then came 2016, and the announcement of Proxima b, and the nearest star became something else entirely. It became the closest possible address for another world, the nearest place outside our own solar system where a planet, a rocky planet, potentially Earth-sized, potentially in the right temperature range for liquid water, might exist. The conversation changed overnight. Not just in scientific circles, but in the broader culture. Proxima b was discussed in newspapers and magazines, and on radio programs, and in casual conversations between people who had never before thought about exoplanets. Because it was close, because 4.2 light-years, while incomprehensibly far in any practical sense, is at least the smallest interstellar distance available to us. Because if we were ever going to send a probe to another star system, this is the one that makes the most sense to go to first. And because the question of whether there is life there, whether the nearest star has a habitable world, is one of the questions that most people, if asked honestly, would most like to know the answer to. The probe that goes to Proxima Centauri, when it goes, if it goes, however it gets there, will not carry passengers. It will be small and light and fast, designed to survive the journey and to collect whatever data it can in the brief flyby window before it has moved too far past the system to continue measuring. It will carry cameras and spectrometers and whatever instruments the engineers of its era can fit into its tiny frame, and it will send back whatever it finds. Images of Proxima b, if the orbit is right and the timing works out. Spectral data about any atmosphere, magnetic field measurements, particle environment data. Everything it can measure in the minutes or hours of close approach. And then it will continue, past Proxima Centauri, past the edges of that star's gravitational influence, out into the interstellar medium on the far side, moving away from both solar systems at once, carrying its data already sent, its mission already complete, heading into the open space between the stars with nothing ahead of it for a very long time. Like Voyager 1, but further. Like Voyager 1 will eventually be when it has travelled the distance that today we can only imagine crossing. The data from that probe will take 4.2 years to return. Someone will be waiting for it. They will have grown 4 years older since the probe passed through the system. The world they live in will have changed in 4 years of ways they could not fully predict. And then the data will arrive at the speed of light. And the question that has been open since 1915, what is the nearest star like up close, and what surrounds it, will begin to receive its answer. That moment has not happened yet. It may happen within your lifetime, or your children's, or your grandchildren's. The timescale depends on how seriously our civilization takes the challenge, how much of its resources and ingenuity it directs toward the problem, how quickly the engineering obstacles are solved, but the physics permits it. The distance, though vast by any human measure, is the minimum interstellar distance available to us. If we are going anywhere, we will probably go there first, and then further, because that is how the story seems to go. We go as far as we can with the tools we have, and then we build better tools, and then we go further. From Earth to the Moon, from the inner solar system to the outer planets. From the outer planets to the heliopause. From the heliopause to the nearest star, each step enormously larger than the one before. Each step taking longer to complete. Each step requiring technologies that could not have been built at the previous step. But the direction is consistent. Outward, away from the familiar, toward the unknown. The stars are patient. They do not wait for us. They simply continue, burning at their own pace, on their own schedules, indifferent to whether we arrive. But in their patience there is a kind of invitation. The nearest star will be there when we are ready. The questions about Proxima b will still be open when we have the instruments to answer them. The distances, vast as they are real distances, not symbolic ones, not metaphorical ones, but physical spaces that light crosses in measurable time, that spacecraft can cross in principle, that represent the actual geography of the future. The nearest star is 4.2 light-years away. The next nearest is 4.3, and beyond those, hundreds of stars within 10 light-years, thousands within 50, millions within 1,000. The galaxy extends in every direction for 50,000 light-years from where we sit, full of suns and worlds, and everything that orbits and burns and drifts. Most of it entirely unknown, none of it inaccessible in principle, all of it waiting. Waiting, that is the word for it. The universe is waiting. Not with impatience. The universe does not have impatience. It is simply there, as it has always been, as it will continue to be. The questions are open, the distances are real, the light is travelling, and here on this small world, something has developed the capacity to ask about it all, to wonder, to build instruments, to point them at the sky, and to feel. Lying in the dark at the end of a long day, something that is neither small nor lost but placed, situated, part of a story that is very old and very large, and still, somehow, early. The nearest star burns on, the room is quiet, the day is gone. What remains is this: the particular weight of a body at rest, the particular quality of a mind that has travelled 4.2 light-years and back, and arrived somewhere quieter than where it started. The questions are still open. They will still be open tomorrow. The nearest star will still be burning 4.2 light-years away, small and red and patient, orbited by at least one world, surrounded by the thin silence of interstellar space, its light already on its way here, arriving 4 years from now, carrying whatever news the nearest star has to share. You do not need to hold any of it tonight. The universe is large enough to hold it for you. Rest now. And tomorrow night, there is more. The stars beyond Proxima, the questions those stars carry, the distances that make this one seem close by comparison. The story continues. It always continues. And wherever it goes next, it goes from here, from this quiet room, from this particular arrangement of ancient stellar material that has been wondering about the sky since long before it knew what the sky was. The nearest star is burning, and you are arresting both true at once, both continuing, both exactly as they should be.